In this screencast, I'd like to work through an example of how we can differentiate a function that's been given implicitly. So remember, this would be a problem like this, where we're asked to find the slope of the tangent line to a curve of this form that we really don't want to solve for y. So we have this sort of goofy looking shape here that fails the graph we see fails the vertical line test, and so we know that we can't find a way to express y as a function, as a single function of x, just like with a circle. But there's a big theorem in mathematics called the implicit function theorem that says as long as we're locally linear anywhere around here, and if we were to zoom in, this would look very locally linear, we can think of y as being a function of x there, even though we won't have an explicit formula for y in terms of x. We're just going to treat y as a function of x. And here we've been asked to find the slope of the tangent line at the point -1, 1, which is right here. And so we're really saying, what's the slope of this tangent line? So let's come over here and work through this. So what we're going to do is we're going to differentiate both sides with respect to x, because we're thinking of x as our independent variable, and y we're going to treat as a function of x. And so how we're going to do that is really the chain rule. The number one thing why students seem to make implicit differentiation seem harder than it needs to be is they don't see that it is the chain rule. So hopefully the previous screencast where we wrote, instead of y, we wrote f of x, will help you get a feel for how the chain rule is applied here. So now I just want to come in and start using the sum rule here, and then we've got a power rule, so this is 4x cubed. Now here, x squared is a function of x, and y is a function of x. So here we need a product rule, so we'll go with x squared, we'll leave that alone, and then we get dy dx, which you might also write as y prime, but I'm going to skip that. Then we need to differentiate the x squared, gives us 2x, and then we leave the y alone. And now here's where we really see the chain rule in action, because here we've got an outside function, so we see y to the fourth. We can look at that as y to the fourth there, so our outside function is raising to the fourth power, and our inside function is y, which remember, that's a function of x. So I need to do 4y cubed, that's derivative of the outside function with the inside function left alone in there, times the derivative of the inside function, which all we know about that is that's dy dx. Now, 1 is a constant, so this thing equals 0. At this point, we've been asked a specific question. We've been asked to find the slope of the tangent line at this point. So, rather than solving for a general form for dy dx here, where we might make a great big mess of this, I want to find slope at -1, 1, substitute x equals -1, y equals 1, solve for dy dx. Okay, so if I do that, I get 4 times -1 cubed minus -1 squared dy dx plus 2 times -1 times 1 plus 4 times 1 cubed times dy dx equals 0. So this is -4 minus, and here we get dy dx, minus 2 plus 4 dy dx equals 0. So let's see, we've got a -4, and distributing that minus sign gives us a +2, so that means we've got a -2 over here, and then there's a minus dy dx plus 4 dy dx, so that's plus 3 dy dx equals 0. So moving that 2 over and dividing by 3 gives us dy dx equals 2/3. So this is the slope of the tangent line at -1, 1. Now, why did I recommend substituting in rather than trying to solve this monstrosity for dy dx? You're more likely to make algebra mistakes, and if all you need is the slope of the tangent line at a specific point, then you should just go ahead and do that. But now, what if I asked you a slightly different question? What if instead I asked you to find where the tangent line to this curve is horizontal and where it's vertical? Now we look at it, we're expecting something around here, expecting something around here, expecting something down here, expecting something here for horizontals, and it looks like we're going to have some vertical situations there. So let's go ahead and see what we can do about that. So here's the derivative we worked out earlier, written down in a slightly different order than I wrote it a moment ago, but that's okay. So now we really need to go after this solving for dy dx. So first thing I'm going to do is I'm going to move anything that doesn't have a dy dx in to the other side. And so that's going to give me over here, I'm still going to have my x squared dy dx, and I'm going to have a plus 4y cubed dy dx. To the other side, I'm going to move this 4x cubed, and so I'll get a minus 4x cubed. So I have a minus 2xy, so I move that to the other side, I get plus 2xy. Now, I'm going to factor out a dy dx here, and so I'm going to see that this is really dy dx times x squared plus 4y cubed. So if I divide this piece off, I get dy dx equals minus 4x cubed plus 2xy divided by x squared plus 4y cubed. So now we need to figure out what exactly could give us a situation here where the tangent line is horizontal. Well, the tangent line's horizontal provided that this numerator is 0, and the denominator is not 0. So we look at this and we certainly see that x equals 0 is going to be something that fits that category. If we jump back to our picture here, we see a couple of points where x is 0, where we have that horizontal tangent going on. And then we have, so we need to look at minus 4x cubed plus 2yx equals 0. So that tells us that x times 2y minus 4x squared equals 0. So either x is 0 or 2y equals 4x squared, which would be y equals 2x squared. And now we can drop that expression for y up here into the equation for our curve and figure out what values of x would give us those other 2 points. We also need to find the y values that would work out here. So we put in x for x equals 0. We put in x equals 0 up here, and we want to find out that we're looking at y to the 4th equals 1, so we need y equals plus or minus 1. And the vertical tangent is the numerator is not 0 and the denominator is 0. So we need to look for x squared plus 4y cubed equals 0, or x squared equals minus 4y cubed, which again, we could come and we can put that into the equation for our curve, because we see an x to the fourth, that's x squared squared, and here we've got an x squared, and then you could solve for y to find out specifically where these two vertical tangents are. That's a bit messy on the algebra, so I'm not going to go into the details right here, but I wanted to make the distinction carefully between problems where you're asked for the slope of the tangent line at a specific point, in which case I would never solve this for dy dx and make a mess of my algebra, or this type of problem where I need to find out horizontal tangents, vertical tangents. The only way to do that is to find an expression for dy dx and analyze it carefully to see where the numerator is 0 and the denominator is not, or vice versa. Hope you found this helpful.